problem of fatigue in aircraft structures has been under investigation for many years. Much work has been accomplished in testing and evaluating the effects of different cyclic loads, primarily upon material coupons, typical joints, and small component parts. Although this type of testing, along with service experience, has established the basis of present-day fatigue knowledge, it does not reproduce the complex load conditions which exist in a full-scale aircraft structure. Only in testing of a complete aircraft structure for a given condition can the life relationship of the assembled parts and the influence of these parts on adjoining structure be determined. In service, an airplane is subjected to many different loads, all of which contribute to fatigue of the structure. For the particular wing being tested, it was determined that the greatest portion of the structure is affected by flight loads, and a high proportion of the accumulated fatigue damage could be expected from the large number of cycles that would have to be sustained when flying at 1G, encountering gusts of plus and minus 8 feet per second. Testing was performed at Convair's Structures Test Facility, which is essentially a huge test jig capable of reacting large forces in the floor, walls, and ceiling. Instrumentation for load control was from within the operations building. In flight, loads are normally applied over the wingspan as a distributed load. For the purposes of this test, the loads were summed and applied at 6 stations, located so that the load effect remained correct. These loads were applied by hydraulic cylinders, and measurements of wing deflection versus load magnitude were taken. Using the load deflection data from the static test, springs were designed that had corresponding load deflection rates. These springs were substituted for the load cylinders. A mass of lead equivalent to the 1G load was placed on the wing, and the system resonated to give the desired cyclic load. The wing test specimen consisted of a complete structural box section. Only leading edges, nacelles, and trailing edges were omitted. However, the attachment fittings and cutouts for these assemblies were provided. The test utilized a modified resonant beam system. Loads were introduced through calibrated springs, which contribute the proper loads as the wing deflected. Before this cyclic test could be performed, it was necessary to run a static calibration. Loads were applied by hydraulic cylinders pulling up along the wingspan and down at the fuselage mounts. Hydraulic pressures to the loading cylinders were controlled by an Edison load unit. Loads of 1G plus and minus 8 feet per second were applied, with the proper loads applied simultaneously to all hydraulic cylinders. Under load, the wing was deflected down. Wing bending deflections of the front and rear spars were observed on remote reading Autoson deflection indicators. These instruments accurately indicated deflections to 0.02 of an inch. Deflections were taken from spar clips and transmitted by the Autoson deflection transmitter. Magnitude of load was monitored by electric strain gauge dynamometers. The dynamometers, along with 20 wing spar strains, were recorded using a Baldwin SR4 indicator. Using the load deflection data from the static calibration, springs were designed that matched this load deflection rate. These springs were individually calibrated to ensure that the rate was duplicated. The calibrated springs were substituted for the hydraulic cylinders, and the system resonated. Now the springs contributed the proper loads as the wing was deflected. Complete cycles of load were applied at the rate of 60 cycles per minute. Approximately 8 inches of deflection was experienced per cycle from the high to low position. During test, the structure was under constant visual surveillance for cracks and failures. Inspection holes were cut in the wing spar webs, so located that all internal stringers and fittings could be observed from outside the wing. Since a resonant-type system was utilized, it was necessary to apply exactly that amount of power to overcome wing dampening. Regulated factory air powered the cylinders and was sequenced to the cylinders by a 4-way valve attached mechanically to the wing. In order to prevent resonance in the chord direction, parallel bars were attached to the upper and lower spar rails at the torsional null point. These bars contributed no load to the structure. Their function was as restrainers only. For safety, a sliding restrainer attached to the hydraulic cylinders was employed. In event of failure, the structure would be caught and snubbed by the safety catch. It is interesting to note the bending curvature of the lower spar rail. The load dynamometers and wing spar strains were monitored to ensure correct duplication of the desired loads. The loads, strains, and wing deflections remained consistent during testing. A program for complete periodic inspection was also established, including a thorough daily external inspection. In addition, after every 50,000 cycles, all access doors were removed for internal inspection. These inspections were accomplished using such aids as magnifying glasses. Only after 180,000 cycles were fatigue cracks found. Suspicious areas were then checked with dye penetrant by spraying the dye over the surface and allowing it to penetrate. The excess was then wiped off and caulk was sprayed over the area. The red dye leached into the caulk where cracks were present. Other fatigue cracks were found and evaluated. Cracks appeared at the corners of the access door reinforcement doubler and were propagated through the lower surface skin, emanating from the end rivet. These cracks were then repaired with maintenance-type fixes. Stop holes were drilled in the cracks and internal tapered doublers added to reinforce the area. The repairs were then evaluated by subsequent cycling. Preventive fixes were also tried, such as using double rivets to reduce the stress concentration on what would normally be the end rivet. Evaluations were also made of a rivet added in front of the internal doubler in an attempt to reduce the stress concentration on the end rivet. The end rivets were replaced with very soft rivets in another area. These preventive fixes were all evaluated, and from these tests, corrective action was taken. Convair undertook this fatigue test program in order to evaluate a complete wing under fatigue conditions. Evaluations of failures, causes, and repair methods were made. The information obtained was used in conjunction with element-type tests to perfect those design practices which were fatigue-prone. It is from the lessons learned here that new designs and techniques emanate. has established the basis of present-day fatigue knowledge, it does not reproduce the complex load conditions which exist in a full-scale aircraft structure. Only in testing of a complete aircraft. The problem of fatigue in aircraft structures has been under investigation for many years. Much work has been accomplished in testing and evaluating the effects of different cyclic loads, primarily upon material coupons, typical joints, and small component parts. Although this type of testing, along with service experience of structure for a given condition, can the life relationship of the assembled parts and the influence of these parts on adjoining structure be determined. In service, an airplane is subject